Hello and welcome to 5-2 Polynomials, Linear Factors, and Zeros. Your warm-up answers are on here. So for number 1, 1 over x to the 11th. For number 2, if you're looking at the graph, as x is approaching, f of x is approaching positive infinity, so this is positive side over here as it's going up. It's on the left side of the graph, so x is approaching negative infinity. And then on this side of the graph, as f of x is approaching negative infinity, x is approaching positive infinity because it's on the right side of the graph there. Okay, so today, some new stuff for us. Our SWABAT is to analyze the factored form of polynomials and write polynomial functions from its zeros. Lots of fun for us today. Key concept: roots, zeros, and exponents. Spoiler alert, they're all the same thing. So this could be intimidating, but for us it's not. We just know that they're saying this is a polynomial written in standard form from the highest degree to the least degree, which could be a constant, quite possibly. Some equivalent statements. Well, here's what we did before. When we had a factor, x minus b, and we set it equal to 0, we found that x was equal to b, if you add b to both sides. That b that we have right here is the same thing as saying that b is a 0. That's why we use the 0 function when we're finding zeros or finding the x-intercepts on our calculators. It's also known as a root or solutions, and it's also known as the x-intercept. All of these words kind of are referring to the exact same thing, so don't get tripped up by that. So today we're going to start our wonderful graphing tour of this, and we have our steps here. Step 1, find the zeros, also known as roots, also known as solutions, also known as x-intercepts. Step 2, find additional points either both between and beyond. So if this is an intercept and this is an intercept, I want points between and beyond them. Finally, determine the end behavior, which is what we looked at up here. So for number 1, find the zeros of each function, and then you have this function that's given, then graph the function. So find the zeros also known as x-intercept. So I can do that by, remember that x-intercepts happen when y equals 0. So I can set each of these equal to 0. So 0 equals this. X plus 1 equals 0, x minus 1 equals 0, and x minus 3 is equal to 0. So x equals negative 1. 1 when you solve this one. If you add 3 both sides, you get 3 for that one. So I won't write these each as coordinates, but I will graph them really quickly. So this is negative 1, positive 1, and 1, 2, 3. Those are your zeros. Go ahead and plot each of them, and let's go ahead and label them as well. So step 1, check points between and beyond. So I'm going to make an XY table. Beyond. So beyond means points to the left of these. I'm going to tell you, you need a good 6 points, so don't be shy. I'm going to go for, after negative 1, I'll hit negative 2. Between negative 1 and 1 is 0. What's a number between 1 and 3? You can use a half. You can use 1.5. You can't use a half. Sorry, you can use 1.5. You can use 2.9. As long as you pick any number in between there. I am, of course, going to use the number 2 because it's easier for me to deal with. And then beyond, a number after 3, 4. Okay, if you could please take a moment and you can plug these into your calculators, or you could also trust me and you can trust my math and know that when I plugged in negative 2, I got negative 15. For 0, I get 3. When I plug in 2, I get negative 3, and for 4, I get 15. Now I'm looking at this, as you might be also, and you're thinking, okay, it's not going to fit. So we're going to change the scale, and 1, 2, 3, 4, 5. There's 5 lines in each direction, so I'm going to go by 3s. I'm going to note that I'm going by 3s by just putting a 3 right there. So go ahead and plot negative 2, and this is 3, 6, 9, 12, 15. 0, 3 is right here. 2, negative 3 is here, and then 4, 15. Did you catch my mistake before I did? Probably. This is wrong. This was negative 2, negative 15. Yeah, I guess you are paying attention. 1, 2, 3, 4, 5, down. There it is. Sorry about that. Then from here, determine the end behavior. Well, this is x times x times x, which gives me x cubed. It's an odd function, so it should end in two different directions, and because it's positive, it ends in a high note. So I'm going to go ahead and say this is my end, which kind of matches, which is great. So this will continue to skyrocket. This will approach negative infinity as well. As long as you've labeled your key points on your axes, then I am one happy camper. Okay, letter B. I have x plus 4 squared times x plus 1. We're going to go ahead and go with step 1, and that is to find the zeros. So I set this equal to 0. X plus 4 squared equals 0. X plus 1 equals 0. You can square root both sides. X plus 4 equals typically plus or minus. But because it's just 0, we don't need that. So x equals negative 4. And for this equation, x equals negative 1. So negative 1, 2, 3, and negative 4. Grand. Now, negative 1, negative 4. I'm going to label now because, truth be told, sometimes I forget, and I think some of you are already judging me for my last mistake, and I don't want to make another one. So, points between and beyond. Well, here's beyond. For my xy table, I'm going to go ahead and do negative 5. Between, pick a number between negative 1 and negative 4. No one cares which one you do. I'm going to go ahead and go for negative 2. I'm also going to do negative 3 as well, just because there's a lot of space here and I want to see what's happening. And there's only 2 points, so I'm going to go with 0 also. Okay, then you plug them in to this equation. So when I plug in negative 5 into here, I get negative 4. When I plug in negative 2, I got negative 4. When I plug in negative 3, I get negative 2, which makes me feel like, cool, maybe I don't have to change the scale. And then for the last point, I plug in 0 and I get 16, which makes me think, yes, I do. I'm going to go by 4s. And so for negative 5, I have negative 4. Oh, let's talk about your end behavior. This is x to the second power, so that's x squared times x. So I'm getting x cubed, and it's positive as well. So it will end on a positive note, and because it's odd, it's going in a different direction there. My points between. At negative 5 was negative 4. And at negative 3 was negative 2, so that's just halfway there, because I went by 4s. And then what was 0? 16. And there we go. Then we'll connect our dots. Interesting. I'm only touching right there. You can't go through it and then come back down, because that would be making up points that don't actually exist. Another thing that I'm going to call your attention to right here, this negative 4, it only touches the axis and then it bounces right back. Notice that. It's because this is squared. So if it was like second power to the 4th, 6th, 8th power, if the degree is even of just this one factor, then it's going to touch the axis. If it's odd, it will actually cross it, which is what we've been seeing for the odd ones that we've had there. Okay, bueno. Next thing is the factor theorem. The expression x minus a is a factor of the polynomial if and only if the value of a is a 0. Makes sense because when we had this as a factor, we would solve it and find that x equals a of the related polynomial. Write the polynomial function in standard form with the given of the polynomial with the given zeros. So, what would this be as a factor? Well, if I told you instead, oh, hey, x equals b, then as a factor, it's x minus b. If I tell you x equals 2, then as a factor, it's x minus 2. If I tell you x equals negative 3, then as a factor, x plus 3. Little dramatic pause there for you. So, what are these as factors? Well, the first one would be x plus 1, because notice we're changing the signs. X minus 3, times x minus 4. This is what you can use y, you can use f of x, whichever one you absolutely positively prefer. Well, what's next, Misfits? Next, I'm going to multiply. Just that basic. So I'm going to FOIL these out, and I get x squared minus 2x minus 3. I FOIL well in my head. You can always show that out if you'd like to. Now, I'm going to just give you a hint. When I have these, sometimes it really does get a little bit complicated. So I will use the box method. Also kind of looks like a Punnett square. And so this is x squared negative 2x minus 3. X times x squared is x cubed. X times negative 2x is negative 2x squared. X times negative 3, negative 3x. X squared times negative 4, negative 4x squared. Negative 4 times negative 2x is 8x. Negative 4 times negative 3 is 12. What I like about this box is that my like terms are on my diagonals, right here and right here. So I'm going to have x cubed, and then negative 4x squared minus 2x squared is negative 6x squared. 8x minus 3x plus 5x, and then plus 12. All of this is equal to y, or you can also use f of x. Okay, I'm going to set you up for part B. My factors will be x plus 3 times x plus 0. I'm not going to write that plus 0. And then x plus 0. Oh, snap. I just said I wasn't going to write it. And then x minus 5. Well, what I like about this is that it's just x squared times x plus 3 times x minus 5. I believe you can FOIL this out and then multiply that. Press pause, and you can check your answer with my answer. I don't know if you really press pause or not, but this would be my correct answer. I did change it just to f of x, just so that you can see it does not matter which one you use, f of x or y. Your teachers are happy with both. Okay, so now I'm kind of doing the opposite a little bit. This is equal to 0. We're going to find the roots. So x minus 1 equals 0, x plus 2 squared equals 0. Same thing that we just did for the last one. So we see that x is equal to 1 and negative 2. This is my repeated root. How many times is it repeated? Twice, which means that it will touch the axis. This is a repeated root 3 times, so I would take the cubed root actually. So 0, you don't have to worry about that yet. Minus 5, so x equals 5. It's an odd degree, so it's repeated, but it will go through the axis. Goes through the axis. And then lastly for this one, x equals 0. Don't forget to make it just 0 for that one. And then for this one it would be positive 8. This one's repeated, and it will touch the axis. Okay. Bueno. Last example for this video is turning points. That's when you're changing from one direction to the other. It's like repentance. So f of x, the degree of n has at most n minus 1 turning points. If f of x has n distinct real roots, then it has exactly n. The distinct meanings there aren't any repeat ones, as we saw there. So we're going to pause here for now and look at this graph and see if we can tell, okay, we were going in this direction, we changed, so this is one turning point because we went from up to down. Here's another turning point because I was going down, now I'm going up. That's 2. I was going up, now I'm going down. That's 3. I was going down, now I'm going up. So there are 4. 1, 2, 3, 4 turning points. So if there are 4 turning points, and there's always one more degree, the degree of this one would be 5. Let me ask you, what would the leading coefficient be? Well, because we end on a positive note, the leading coefficient would be a positive number. That's it. For this one, there's one turning point, There's always one more. So if there's one